All right, good morning. Welcome to Grokking HTTP. I am Ben Ramsey. I work for a company called Moontoast. We have a SaaS platform that enables brands to create social rich media ad units that they can use to distribute them to the social stream, to engage with their fans, and then measure their success. I actually usually bring some stickers with me. You can maybe see one on my laptop here, but I didn't have them with me. But if you're interested in getting a sticker, just send me an email to ben@moontoast.com or ben@benramsey.com, and I'll be happy to send you a sticker. A little bit more about me. This is RAR here. If anyone ever follows me on Twitter or on Facebook, you might have seen pictures of RAR. RAR is a little friend I carry around with me to all my presentations and to all my conferences, and I take pictures and post them on his own Facebook fan page that my son follows. So he gets to kind of follow along with what I'm doing. So if you happen to take a picture of him while I'm up here, please send that to me as well, because I'd like to keep track of that. So today we're talking about HTTP, and I give this talk a lot, but it's not the same talk. I always do variations on it, and I think that it's getting better, and I'm able to put all the little pieces together. So this one, we're going to start off talking a little bit about some basics and an overview of the HTTP protocol. That's a little redundant there. But then I'm going to go into some more advanced things that I usually save just for one slide and say, here are advanced topics. I'm going to go a little deeper into those today. And then at the end, we'll talk a little bit about where HTTP is going and in the future. So I love the word Grok. This is a good word. It means to understand. But it's more than just understanding. It's being one with the thing that you're understanding. So the word comes from a book by Robert Heinlein called Stranger in a Strange Land. It's a story about a human, Michael Valentine, who was raised by Martians on Mars. And then humans went back to Mars, and they found him, and he had grown up by this time, and they decided, we'll bring him back to Earth. And so they brought him back to Earth, but being raised by Martians, he was unaccustomed to Am I back? Excellent. That was a great fanfare. Thank you. I'm happy to be here. So Michael Valentine has come to Earth. He's got to adjust to human culture, but he's learned all this stuff about being a Martian. And part about being a Martian is that I guess he's using more of his brain than humans normally use, because he's able to do interesting things like slow down body processes just at will, and also to grok things and to grok people. And in grokking something, it means that he's come to an intimate understanding of that thing. And so the reason I like this word is because I like it in terms of technology. It's one of those aha moments where you suddenly just kind of grasp the concept of what it is you're working with. And now you understand it. But before then, it was all this kind of confusion. So to grok, according to Wikipedia, means to intimately and completely share the same reality or line of thinking with another physical or conceptual entity. So I like to use that word when talking about HTTP. But are you really going to fully understand and grok HTTP after this talk? I don't think I can help you do that. That's something that you have to do on your own. But what I hope you'll get out of this is a better understanding of the protocol of the web, and you'll have some gems to take home with you that'll kind of spark your imagination and get you digging more into it. So let's start with the basics. What is HTTP? Well, HTTP is the hypertext transfer protocol. It was defined and formalized in the RFC, which is a request for comments, 2616. And there's a bunch of other RFCs that go along with that. This one obsoletes some earlier ones. There were earlier versions of HTTP. Right now, the current version we're using is 1.1, and that's been around since 1999 in its current form. So not a lot changed since then. But we'll talk a little bit more about changes that are coming. Hypertext, it deals with hypertext. So Tim Berners-Lee had this concept of the web as a web of links. And in order to create these links and in order to have things that link to each other, we needed hypertext. So hypertext is, according to this definition, I'll just read it here, a multilinear set of objects, building a network by using logical links. And these are the hyperlinks. So if you think about HTML, it has an A tag, and that represents a hyperlink to another document. And when you click on that link, it represents a state change, and you go to that document within your browser. HTTP is a set of rules for transferring hypertext across the internet. It forms the basis of everything we do on the web. It is the web. If you're not sending data over HTTP, you're not sending data over the web. And likewise, if you're sending data over HTTP, you are sending data over the web. So let's take a quick look at what that looks like. And again, this is pretty basic. So I open up my web browser, and I go to that address bar and type in benramsey.com. What the web browser does in the background now is it sends a request that looks a lot like this. This is a GET request. I'll talk about this a little bit more detail in a few minutes. And there's some other information in here. What we have on that first line is the actual method that we're calling. And included in that method is the path that we want to act on. And this path is just slash. So it's the root path. And then there's the version of HTTP. But below that are a bunch of headers. And these are headers that our browser sends along with the request to tell the server some details about what it can do and what kinds of content it can receive. And also how to cache it and so forth. So what you get back is a page that looks like this. And the browser takes all of the data that was in the response and knows how to render it. And that response looks a lot like this, and this is truncated. But the top there tells what version of HTTP that the server was using and gives a status message along with a number. And that number in this case is 200, and the status is OK. Again, we have a bunch of headers that are there to indicate to the client or to proxies along the way things that can be done with this data. And then below that, we have the actual hypertext content. And in this case, it's HTML, but it could be something else. So one of the big questions I often get, especially from newcomers, is how do I see all of that? You're looking at this. Now, there are many different ways to see all this information. One of the easiest ways is to use the browser. Most browsers nowadays have built-in consoles that allow you to, well, first of all, they allow you to view the source, but then you can also use your browser console in Chrome or Firefox or Safari to look at the actual communication that's going on and to see the headers. But in addition to those tools, I have some favorite tools that I want to recommend. And these are additional to the browser toolbars and consoles. The first one is called Charles. I cannot recommend this tool enough. And I don't use it a whole lot right now, but I was using this very frequently when I was dealing with some Flash communication. So we needed to have Flash applications running in the browser that would send requests to an API. And in order to debug that, I couldn't see any of that within a browser console. So I needed a different tool, and Charles provided that. Charles is actually a proxy. It takes over the communication in your computer across the network, and then you can inspect all of that communication. There are other network inspectors out there. One of the big, oldest ones around that I'm aware of is Wireshark, which Wireshark may be the new name. I think it used to be called by a different name. But at any rate, it's another network inspector. And there are others out there, too. So it's really kind of personal preference. But with Charles, I found it really easy because it breaks down the headers and it breaks down even the content you get back. So in the example screenshot that you see here, you'll see that it's actually taking a JSON response and breaking it down into a hierarchical tree. But you can also look at it in the raw, and you can also look at the big thing that we used it for was with Flash AMF remoting. We were able to see the AMF object in the communication here and see exactly what data was included in it. And it was very helpful for debugging. And then, rather than having to make the request from Flash again to see what the server would send me, I could just modify the request in Charles and then tell it to send it again. And it would send it just as if Flash had sent it. So it was really helpful. Well worth the $50. But the other one that I really like is called HeadyPy. At least I think that's how it's pronounced. So the Python community tells me. HeadyPy is better than curl. So stop using curl. Curl works. It's good. But HeadyPy makes it easier. It's kind of curl for humans. So if you go to headypy.org, this is actually just all on GitHub. That'll redirect you to the GitHub project. And it's perfect for testing and debugging APIs. It's just a command line tool, and it's free. It's really good. All right, so that's what I like to use, and those are my recommendations for how to look at the messages we're sending back and forth. So now let's talk about the protocol. HTTP has these properties. It's built with a client-server architecture. It's atomic. All the requests are self-contained. They don't need to rely on other requests. It's cacheable, so resources can tell clients along the way, including proxies, how to cache them and how long their data is considered fresh. It has a uniform interface, so the clients and servers all understand the same interface, which includes methods and content types and metadata. It's a layered system. This is really important because caching can take place at any layer in the system. A proxy can respect a cache control header, and it might be between your computer and the server, and then the next request you make might go to the proxy, but it might not go all the way to the server, depending on the caching rules. And then it also provides the ability for code on demand. And this allows HTTP to deliver scripts and other code, such as JavaScript and CSS, that provide other information about how to process the data. So a web page with JavaScript, and that web page now has extra functionality that the browser would not have otherwise been able to provide for it, because you've given it to it through JavaScript. And what does this all sound like? HTTP is a RESTful protocol. In fact, these are all the constraints that REST defines, and in fact, REST was defined based on the work that went into HTTP. So Roy Fielding, when he created his REST doctoral dissertation, or the doctoral dissertation on which he defined REST, was drawing on all the experiences that he had in building HTTP with the greater community. All right, so RFC 2616, this is the de facto HTTP standard right now, defines these 8 headers, or I'm sorry, methods. And a method is basically just an action that you're going to take on a resource. And we'll go into detail on some of these. I won't go into detail on options, trace, and connect, but these are dealing mainly with the proxies. This isn't all the headers that HTTP has, by the way, and we'll talk about that a little bit more. But before I talk about some of the headers, I want to take a moment to talk about 2 special terms that we need to be aware of. The first one is safe methods, and the second one is idempotents. And I'll get to that in just a minute. But a safe method is defined in the RFC as being a method that should not have any other action than retrieval. I'm sorry. I have the definition right here. In particular, okay, let me read that in just a minute. So get and head are considered safe. I think they're the only methods in the RFC considered safe. And that's because they should take no action other than retrieval. That means that they don't have side effects on the server. So when you call these methods, the implication is that the server the state of the server doesn't change by the nature that you call these methods. The reason for that is that the user isn't requesting side effects when they make a GET request. They're not requesting that any data on the server changes. Now, we kind of violate this rule a lot, and the reason we violate it is because we have things like counters and other things like, maybe we use a GET request to send query string parameters that will increase a vote count or something like that on the server. These break the safe nature of these methods because the user may not have intended those side effects to happen on the server, and the state of the server changed. This came into play a few years ago, maybe more than a few years ago now. Who remembers Google Web Accelerator? All right, so a few people. So Google came out with this tool that was basically a browser plugin or a browser toolbar called Google Web Accelerator. What it was a way to, when you loaded a web page, it would go ahead and read off all the links on that page and go ahead and request everything else in the background and cache it. This way, when you clicked one of those links, you were retrieving it from your local cache, and it was really fast, or it looked or appeared fast, right? Pretty cool concept, and they were banking on the fact that all of these URLs that they might call were safe methods, or because they were using GET to retrieve them. What happened, though, was that people who built web pages didn't always treat GET as a safe method, right? So on let's just consider, for example, that you've got a page that you've logged into some admin tool, and you've got a list of blog posts, right? And in that list of blog posts, off to the side is a delete link. And this is a GET request, possibly, because it's just an A tag. Looks something like this, right? And when I click on that, it's going to delete whatever it was that I told it to delete after it sends this request to the server. The problem is, Google Web Accelerator had no idea that this wasn't safe to do. So it requested it. And all your books or all of your posts got deleted. So GET and head should have no action other than retrieval because of this kind of stuff. So if you follow the protocol, then your pages can be safe, or actions can be considered safe. The next thing is called idempotence. And what this means is a mathematical term, not a sexual dysfunction or anything like that. It means that side effects of n greater than 0 identical requests is the same as for a single request. And what this means is that when I make a request, it might have side effects, but if I make the same identical requests, the state of the server does not change beyond what it did the first time I made the request. So if I make that request 100 times, the state of the server remains the same as if I only made the request once. So get, head, put, and delete share this property, and options and trace are inherently idempotent. Okay, so those are important because a lot of the methods are either safe or idempotent or both. Get is usually used for retrieval of information. It transfers a representation of the resource from the server to the client, and it is safe, or is supposed to be, and it's idempotent. That means the state of the server is not going to change. This is what a GET request looks like. And I've already kind of gone over that first line. There's the method, there's the path, and there's the version of HTTP you're using. And then there's some method headers below that. And a response that you get back might look something like this. So we say that the response is OK in this case. There are a bunch of other status codes, though. And then there's some details, metadata about what you can do with the request at the client or proxy level, and then there's the body of our request. Head is identical to GET, except that it doesn't return the body. It only returns those headers. So this can be really useful if you just need to find out information such as the size of a file that you're trying to get, or other options about the resource that you want to perform, such as like methods that are allowed and so forth. It is safe and idempotent, and it looks a lot like this. In fact, it's identical to the GET request. The only difference is that we're using the head method instead of the get method. Post. Now, most of us should be familiar with post. If we're not familiar with the other methods, get and post are the methods that we're most familiar with. And this is because web browsers perform these two methods really well. And when post, what it means is that the body content should be accepted as a new subordinate of the resource. So we often use post to process things like forms or creation of new content within an API. Basically means to append or annotate or paste after. It's not safe or idempotent because I could issue the same exact, well, first of all, it's not safe because it does have side effects on the server. It's going to do something. In fact, that's the intent. It's not idempotent because I could issue the same post request multiple times. It might be an identical request, all the headers and everything the same, but the server might do different things with that content. So if I post to like a books resource in an API with a book and the content, it might create that book. If I post it again to the same resource, it might create another record with the same data. So this is what post looks like. I mean, again, we have our method up there at the top, and I'm using a service here called, if you look at the host header, http://ben.org. I'd recommend checking that out. It's got a bunch of endpoints that you can hit, and you can use HeadyPie to make requests of those endpoints. And I've truncated some of the responses down here that are coming back. But in this, we've got our accept headers and our content length. Basically, we're just posting a JSON body here. And http://ben doesn't really do anything with it. Put. So put is the opposite of get. While with get, you're going to retrieve a full representation of the resource, put, you have to put the full representation of the resource up on the server. Now, if you've been building any APIs and you've been interested in putting or updating documents in your API or updating records, and you only want to update a subset of those records, you might be tempted to use post or put to only do a few fields that need to be updated in your API. But that's really not the intent of put in this case. Put is intended to be the full representation of the resource put back up on the server. Now, people also use post to do the semantics of like a partial update, but I will talk about another method later, the patch method, which is a new method that is intended for partial updates. Put's not safe, but it is idempotent. And that's kind of an interesting thing to think about. And we'll talk about that in just a minute. Again, this request looks eerily just like the post request. The only difference is that the method is put. And I'll explain the difference between post and put in just a minute as well. Finally, the last method that I want to cover right here is the delete method. This tells the server to remove a resource from public view, essentially. Doesn't necessarily have to completely delete it from the database or anything like that. That's all up to you on the server side. But it does request that it remove it from public view. It's not safe because side effects happen on the server. But this one, just like put, is also idempotent. And essentially, the main difference here is that you don't have a body. It's sort of like a GET request in that regard, but it has a different method called delete. All right, so I've mentioned that put and delete are idempotent. Why are they idempotent? I mean, the data on the server changes, right? Well, that's right, but the state remains the same for every request. So this is important because if I make a put request to put a document up on the server, and that effectively either creates a document at the resource I've identified, or it updates a document at the resource I've identified, I can make the same identical put request 100 times, and the state of that resource is the same as it was for the first time I made the request. All right? Let that sink in a little bit. Delete's the same way. If I send a delete request for a resource, and the server removes it and deletes it, and I send the same delete request for that same resource 100 more times, the state of the server is going to remain the same. It will have removed the document or the resource, and it's not going to be any different each time I make that request. It's going to be continually removed. Or the server's not going to try to remove it again necessarily, but the state hasn't changed. What's the difference between post and put? Well, the difference is in the URI. So right here, we've got two requests. And this is from like a hypothetical API example. And it's a books API maybe. The first one is a post request. So we're posting to the /books resource, which effectively would create a book in this hypothetical service. But when we want to update that resource, we need to tell it the exact resource to update. So we put it to the actual URI of the resource. So the difference here is that when I post to a resource or to a path, I'm telling the server to create a subordinate of that resource. When I put to the server, I'm telling the server to either create or update the resource at this URI. So this is a long-winded way of saying just what I just said, but the fundamental difference is reflected in the different meaning of the request URI. And that's because the post request, that URI identifies the resource that will handle the enclosed entity. So it's a processing script, essentially. It's going to do something with that data, but it's not necessarily the endpoint at which the data will live when it's created or updated or whatever. But put, on the other hand, identifies the entity, the URI in a put request identifies the entity enclosed with the request, and the user agent, did I just read that wrong? Okay, so on a put request, the user agent, which is the browser, actually knows what resource or what path this resource lives at. And so when you put to a resource, that is, when you put to a URI, that is the URI where that resource lives that you're putting there. So if it doesn't exist yet on the server might create it if you're working with a service that allows that, or if it already exists, the server might update it if it allows that. Okay, I mentioned status codes and I showed 200 OK. There's a lot of status codes. I'm not going to go over all of them. We're just going to briefly run through the high level of what the status codes mean. The 100 series are the informational status codes. The one that gets used possibly the most in modern usage is the 100 continue, which basically is an indicator from the, basically you say, I want to get back 100 continue if the server will process, you send something to the server, you tell it you expect to get back a 100 continue, the server gives you back a 100 continue, and then you can continue sending it. And basically it just means, server, go ahead and take a look at what I'm going to send you, and let me know if it's okay to continue sending it. In practice, I've seen this happen with curl requests mainly, but I've not seen anyone really implement it in an API service. 200 are the successful status codes. So 200 OK, we all know about. There's 204 no content. There's 206. There's a bunch of other 201 created, 202 accepted. There's a bunch of these. All of them mean that the server was successful in doing what you told it to do. 300 are the redirection. So we're probably most familiar with like 301, which is the move permanently. There's 302, which is found. 303, which is see other. 307, which is moved temporarily. And basically the semantics around all of those really just deal with what can be cached. So 301 moved permanently is a cacheable response. A server, like a proxy or the client, can cache that it moved, and then it doesn't have to make that request again. It knows to take the location and redirect every time to that location. It's permanent. But 302 found is not cacheable. The location header could change each time the request is made, so it has to go back to the server to find the location. 400 are client errors. We're familiar with 404 not found. There's 400 just bad request, and then there's a bunch of other 400 series errors that you can use when building a service. And then finally, the 500 series is the server error. So you're familiar with 500 internal server error, but there's a couple others of those that we can use as well. Okay. I want to get deeper into other topics in HTTP that might be of interest to you and might be of interest to applications that you're building. These 4 topics are content negotiation, caching, conditional requests, and range requests. The first one, content negotiation, is also known as, you might see it on mailing lists or in documentation as conneg, or however you pronounce it. It's essentially the process of selecting the best representation for a given response when there's multiple representations available. So most of the time when you make a request to a server, you want to get back an HTML page if it's within the browser, right? What if there are multiple versions that can come back? How do you deal with that? What if you want to receive a different version, like an XML over a JSON representation, if you want to use XML? So there's 2 types of content negotiation that you can use to deal with that. The first one is server-driven negotiation, and the second one is agent-driven negotiation. Server-driven negotiation is obviously where the server makes the determination of what the best possible resource or representation is to send back to you. So earlier examples like the HeadyPie stuff, you might have noticed that the accept header had like */*. Well, that basically tells the server, I'll accept any representation you can give me. But that's not the only way you can do it. You can specify different representations through that. So the client may send headers to help the server guess. And if the server can't fulfill that request, it doesn't have to send an error back. The server can send whatever representation it wants. It's the server's prerogative. There are these headers that are useful in making these kinds of requests. The accept header, accept language, could give you back a different representation based on the language. Accept encoding, accept charset, and then the user agent header can even be used. So we do this a lot with mobile and device detection. We might look at the user agent and give back a different representation for a different kind of user agent. So the server's not limited to those, though. The server could use different factors, maybe the time of day, or different kinds of things that the server might want to use to make that determination. But it's the server's best guess. So it might be a different resource or a different representation that you get back. Same resource, different representation on subsequent requests. An example. I've overloaded this example with just about every accept header you could possibly put in there because I wanted to kind of talk through the accept headers. But basically, in our hypothetical book API here, we've got a GET request to get back a book with this ID or at this path. And we have these accept headers here, accept charset. So I'm telling the server, excuse me, I'm telling the server I want to get back UTF-8 encoded data. All right, the server can respect that if it wants. I'm telling the server in the accept language that I will accept, in fact, my first priority of acceptance is US English because I'm not putting a qualifier on it, so it's automatically Q equals 1. But I'm also saying that I'll accept Great Britain English at a qualifier of 0.8 or 80%, and then just general English, if you don't have that, at 70%, right? And in fact, you can use these quality parameters on different accept headers. Another one that you can use them on is just the general accept header, which you see down there below says application/how plus JSON. So in this case, my quality is 100% on that. It would be Q equals 1.0. But I could specify different content types that I could receive. Like if I also could parse XML, I might say, give me back application/XML, and the quality on that might be 70%. So if the server can't support HAL JSON, but it can support XML, it might choose to send me the XML. And then encoding, I can tell it different encodings that I can decode. So in this case, I'm telling the server, I can decode gzip data, so if you want to do that, then you can send me gzipped encoded data. So the server might send back a response that looks a little bit like this. Important things to note here, the content language. The server said, hey, sure, I can respect your language preference. I'm sending you back, and I have multiple language preferences probably. So I'm sending you back the one that's US English. And there's a vary header. I'll come back to that in just a minute. The content encoding is gzip. So yeah, this data is gzip. I do that. The content type is HAL-JSON, and the char set is UTF-8. So server said, sure, I can handle all that you've requested from me, and I'll give you back exactly what you want. But the server doesn't have to do that if it doesn't want to or doesn't support that. And now going back to the vary header. So you can see I've got a comma-separated list of all these headers. And what this vary header is doing, so just imagine if this data is cacheable at a proxy, and I have said I want the EN-US one, and someone else said they want the Spanish version. It's the same resource, right? The same path, but two different representations, one Spanish and one English. Well, if it caches that at the proxy, and I happen to go through the same proxy as someone else who requested it earlier and got Spanish, and that proxy says, oh, I already have this resource, I'm just going to give it to you without sending the request all the way to the server. Well, I might get the Spanish version, and that would be unfortunate. So the vary header is here to say, let's vary caching rules based on these headers. So if someone sends it and they both have an identical accept header, then we can cache that and we can be pretty certain that when another request comes in with the same accept headers, then I can send that cached version. But if the accept headers vary, then I need to send the request back to the server to get that representation. Agent-driven negotiation. Well, this is similar to server-driven in that there's negotiation going on, but instead of the server making the determination of what to send back, the user agent or the browser or the client, whatever you want to call it, is making the determination on its side. This usually requires multiple requests because the client doesn't know what other representations are available, while the server does. So the server has to tell the client what other representations are available. Now we can do this in multiple ways. The one way in this example is a multi-request way. In fact, it always has to be multiple requests, but we can do it in different ways than my example shows. I'll talk through those after the example. So in the example here, the first request that we get back is going to show a list of resources available and give some more data about what those resources, like what kind of resource it is. And then the user agent can look at that and decide which one to request and present to the user. So again, in our Books API example, I've stripped out all the accept headers, and we're just going to request that URI. And the server says, hey, hold on just a second. I have multiple choices. So 300 is the multiple choices status code. And HTTP does not define what the content should look like in this response. It doesn't set up any kind of content type to say, here's how to represent multiple choices. What I'm using here is HAL-JSON to represent links that also specify other things about the resource. So if you're familiar with link tags, you can have on a link tag the href, which is the link to that resource, hreflang, which is what kind of language, a hint of what kind of language that resource has, the type. You can also put a title and some other stuff in there. So in this example, I'm using HAL because I think it represents links pretty well. And so you could possibly send this back to the client, and it says, okay, here's a relationship, a link relationship, alternate. Then at the bottom, you see the link relationship of self. So let's look at the alternate ones. Under the alternate ones, I've got 3 different choices. The first one says that its hreflang is EN-US, and its type is HTML. The second one says it's EN-US, but its type is HAL-JSON. And then the last one, again, US English, but it's HAL-XML. Now the client says, which one do I want to get back? Well, I want to get the HTML one. So now I make a request to the href on the HTML one. So I mentioned a minute ago that there are different ways of doing this. We're going to talk in a few minutes about web linking. And web linking is a new spec that's out, our new RFC, and it defines ways to represent these kinds of links that you see up here in the headers of the response. So maybe you'd get back a 300 multiple choices, but instead of having HAL JSON, like in my example, in the body, you might have a header that has links in it, represented almost exactly like this, but a different way of doing it. Yes, go ahead. Can you speak up just a bit? How do you define who has the control, like the server versus the client? That's a very good question. There's nothing in HTTP that really defines what the control is. If I sent, it really depends on, if you're talking about like an API service, then if you want to provide multiple choices through the API, then you can do that. If the client can understand that 300 multiple choices and it gets back 300 multiple choices and it can read the content type that it got back, then the control can be on the user agent. But if the user agent wants to specify different things it accepts, then maybe the server can take those and send back its best guess. So it's really kind of up to the service implementer, and that would be you, and how you want to handle that. But there's not a great way to denote at this point whether or not you want the server to make the decision versus the agent making the decision. Does that help? The server, yes, okay, that's a good way of putting it. The server controls it nevertheless, but the server can give options to the client if it wants to. Caching. So HTTP is really good in that it provides caching opportunities, and it provides information. The server can provide information about how to cache something, and the client can even provide information about what kind of data it wants to get back and how, and freshness. And there's two headers that really control all of this. One is the expires header, and one is the cache control header. And the expires header basically just tells all caches how long the associated representation is fresh. And after that time, it needs to make another request to get it back. And so you might have your local browser gets a resource that has the expires header, and it says this is good for 30 days. But the next time your browser makes that request, it doesn't go to the server at all. It just pulls it out of the local cache, unless you've cleared your cache, of course. Proxies can do the same thing. So if your local cache doesn't cache it, then it might still make a request that goes through a proxy, and that proxy might have cached it as well. And then the cache control header specifies directives that must be obeyed by all caching mechanisms along the request-response chain. I'll talk a little bit about these cache properties. So these are all the properties that the cache control header respects and defines. And the first one is max age. It's similar to the expires header, but the expires header gives an actual date at which point the resource is no longer fresh. The max age, however, says this document is good for this number of seconds. It could be like an hour, it could be a week, it could be 30 days again, or whatever time you want to specify. And then the local, the user agent or the proxy will look at the current time plus the current last modified of the document or of the resource, and make a kind of calculation there and decide, okay, it's still fresh or it's not fresh. I need to go back to the server. Smax age is similar to that, but it only applies to shared caches like proxies. So public and private are really important when dealing with cacheable information. If you cache something and you mark it public, or if you say that this can be cached in a public cache, you're saying that you can put this in a proxy somewhere, and the next user that requests it with the same kind of request gets back that cached version. This is bad if you're, well, it's bad if you're not using SSL anyway for logged in users, but if you aren't using SSL for logged in users and you say that it can be cached public and a user's logged in and they see only data that they can see, then if it got cached in a public proxy, then another user that requests the same resource might get back some other user's data. So SSL by nature is not going to be cached at proxies because it's all encrypted and only decrypted on your local client. But if it's a public page and it gets cached at a public proxy, just be aware of what data got cached on that page. Private, on the other hand, tells it not to cache it at the shared proxy, but to cache it in the local browser. And this can be useful for information or pages where the user's logged in. No cache and no store are similar. No cache basically means don't cache it. Don't cache this resource. But no store goes even further and says don't ever store this resource at all. We don't want you to store it locally at all. Must revalidate and proxy revalidate are also similar in that they basically force a proxy to revalidate the cache that it has and forces your local cache to revalidate. Cache control header looks like this. So in this case, our max age is 3600. We're saying that you must be strict in revalidating. Once the max age has been reached, you must revalidate. So a proxy doesn't necessarily have to if we only had max age equals 3600, a proxy might choose to honor that and then go back to get a fresher copy, or it might just stick with what it has based on conditions. But if we say must revalidate, then it has to honor our max age and has to go back to the server once that's been hit. Conditional requests. I'm going to run through these quickly. We're going to run out of time here. If modified sense, so any of the if dash headers, they're all conditional. If they're provided in a request, then the server will try to honor those and say, so for example, if I make a GET request and say, if modified sense, give it back, give me a new one, and I give it that date, well then I might know the time that I got the last copy, and if it hasn't been modified since that date that I gave it, then the server can just respond with a 304 not modified, for example. So I did not show this list up here a minute ago. I thought I was looking at it. I was looking at it on my screen, but not you. All right, this is the example I just mentioned, where we're saying if modified since here's this date, and the server decides, oh, it hasn't been modified, I'm going to just tell you it's not modified, use your local version. This helps, while there was still a request made to the server, so there was network traffic, but the server didn't have to send the full resource, so it didn't have to do as much work. And the network didn't have to transfer as much data. A range request is used when you've got like binary data or something else and you want to get back only a subset of the bytes. You can send a range request. And that looks a lot like this in this example. So we might make a head request first to an image to see if they support range requests. And in this response that we get back, there's that accept ranges header, and it says bytes. So now we know we can send a range request. The next one is pretty much like a regular GET request to get this resource, but we have range in it instead of not having range. And that says bytes equals 0 through 999. So we're getting back the first 1,000 bytes. We get back a 206 partial content. And in this case, the content length is 1,000 instead of the total length. And we have a content range header that says which bytes we got back. And also the total number of bytes. All right, I wanted to spend some time on the future of HTTP because there's actually a lot going on. Earlier I mentioned that RFC 2616 was finalized and published in 1999. But since then, there have been no changes made to that document. Nothing has superseded it. There have been a few additions that have kind of augmented it, but HTTP really hasn't changed. So I want to talk about a few of those additions and then talk about some advancements that are going on to HTTP itself that we'll see a superseding of 2616 here very soon. The first one is the patch header. I mentioned this earlier. This allows for partial updates. The community around HTTP has been looking for partial updates for years. And finally, this got proposed, and they liked the implementation, so it got accepted. It allows you to make partial updates, and you could make a request, such as an options request, to find out what options a resource provides, and it might send you back, in the example here, I'm showing the allow header, which has patch in it, and also an accept patch header. And so the accept patch header says, we accept patches of this content type. So the patch definition does not specify the content type of a patch. It leaves that open. So that can be open to any service. So there's a couple options right now. One that's coming down the line is still being proposed is JSON patch. I really like it. Another one you could just use is the diff, right? Text/diff. But with JSON patch, what you're sending back is a resource. So this is a patch request, actually. And we're telling it using certain operations like replace and add here, and then a path. And there's also a JSON path specification. And so this uses JSON path to patch JSON, or to patch data. In this case, we're going to patch a book. We're going to replace the ISBN, and we're going to add the Amazon identifier. There's another RFC out there, this is 6585, that introduces some more status codes. These three status codes, let's see, 428 precondition required indicates that the server expects this request to be conditional. So right now there's not a way for the server to indicate to the client that they should have sent a conditional request. So in this case, the server can tell the client. 429, too many requests. Previously, we probably really had to send back a 500 server error or something like that, or the one that says that the service is unavailable. I think that's 503. Now, if someone is making too many requests to your server, you could just say, hey, you're sending too many requests. That's a client error, not a server error. And then another client error, 431, request header field's too large. So if you have a certain strict information about how much data should be in a request header sent to your server, now you can indicate to the client that they're sending too much data. This one is one that I'm really excited about, web linking. It defines a framework for typed links not specific to an application. So it introduced the link header. So earlier I pointed out how JSON has this concept of links. The Atom Publishing Protocol has the concept of links. HTML even has a link tag now, and has for many years, that all indicate relationships and other metadata about the resource that's related. Web linking does the same thing. So it looks very similar to those other implementations, but it's a link header. And in this case, we have the URI, and we tell it what the relationship is, and we can also provide a title in this case. And so the user agent, whether it's a browser or you're consuming an API, can choose to use this information to represent to the user, in this case, if it's aware of the previous and next relationships, which are standard relationships, the browser, I could foresee a browser even saying, there's other pages here, and providing you with buttons in the browser itself to go back and forth. Consequently, there is a how browser tool that you can use to point to a how API, so a how JSON API, and it will read these links and represent to you state transitions through the form of buttons to go backward and forward through paginated record sets and so forth. That's called how browser. Another one that's actually not a standard yet, but I think is really cool, so I wanted to mention it, is called the prefer header. And so this allows the client, or this allows the server let me go back. This allows the client to tell the server how it prefers for the data for the response to come back. So there's two that have been proposed within this specification. One is respond async. So in this case, I'm making a post request, and I'm telling the server, go ahead and respond asynchronously. So I don't care if you process it yet. Just send me back a response right away. And so in this case, we've said 202 accepted. We have accepted your request, and we have applied your preference. But we haven't yet done anything with the data. Maybe it went into a queue or something. And that's really kind of up to you on the server side. And we might also provide the location for where it's going to be once it gets created or something like that. Another one is prefer return equals minimal. So this gives the ability to say, I don't want the full resource. I only want minimal, or I want the max or whatever. So give me back a smaller representation in this example than you would normally give me. Now, there's no definition around how much data needs to be in minimal versus the full representation. It's really up to the server to figure that out. But if you are building an API and you say, a user in the minimal example might just have name, email address, and ID. But in the full version might have all sorts of data around it. Like the Twitter API, for example, when you get back when you request a tweet, it also gives the full user object within that. Well, in this case, Twitter doesn't provide this, so don't take this as saying they do. But you could use this preference to say, I only want a minimal representation. And finally, future of HTTP is being governed by the HTTP BIS working group. Now, BIS is a Latin adverb meaning twice. So this is the second working group. They've met before. That's how they created 2616. But now they are working with that to create RFCs to clarify and supersede 1.1. So what they're doing is taking all of 1.1, which is a massive RFC, and distilling it into 6 different RFCs. So there's 6 sections now to HTTP. And each RFC defines a different aspect of it. One defines the messaging layer, the transport. One defines the semantics, so the methods and some of the headers. One defines security. One defines caching. So they're breaking it apart. And when in the future, the very near future actually, because I think this is trying to be solidified by the end of this year, we'll no longer say RFC 2616 to refer to HTTP. We'll have to refer to a whole bunch of different numbers. In addition to that, they're creating registries of method names and authentication schemes so that you'll have a central place where you can go look up the method names that you might want to use and their definitions. And they're drafting what will become HTTP 2.0. And the current draft is actually based on SPDY, S-P-D-Y. So if you're interested in that, there's a link here, and you can go check out the draft. And basically, SPDY, in a nutshell, doesn't change the semantics of HTTP. You'll still use HTTP 1.1, but in the requests and responses, you might see 2.0. And what HTTP 2.0 will do is changes the transport layer. It makes it much more efficient with sending the messages. But wait, there's more. So I've covered a lot here. I've only really kind of nicked the surface, right? There's a lot more going on in HTTP. I've pointed out some of the things that I think are more interesting, but there's a lot more that you might want to get into and get involved with to learn about that you could take advantage in your application. So I recommend you check out the RFC. It's dry reading, but it has everything in there. That's RFC 2616. Check out what's going on with the future of HTTP. Check out some of the creators and the implementers of HTTP. Check out a bunch of the APIs and API work that's going on with HAL and HAL JSON and web linking and all of that. So I encourage you to go do all that. And I appreciate your time. And I'm open for questions right now. I've got just about 20 seconds left, but I do thank you. And I'll be around in case you have any questions as well.